So next, let's discuss what does overfitting look like for a classifier. So we talked about a wide range of classifiers. So for example, here I'm fitting a linear classifier to the data, and it's our usual example with predicting the review, whether a review is positive or negative for a restaurant. And so we see that the points below the line have score greater than 0, the points above the line have scored less than 0, so below the line I predict is positive, above the line I predict is negative, and you get this very, very simple line in this simple example. For this module, I've created a simple data set shown here on the lower left with positive and negative examples, and I want to fit a bunch of different logistic regression classifiers to it to really observe how overfitting happens in practice. So first, I'm going to fit a simple classifier with linear features. So there's just the constant W0, the coefficient of x1, which is going to be W1, and the coefficient of x2, which is going to be W2. And if I learn a logistic regression classifier on this data, I get the following results. The constant becomes 0.23, the coefficient of x1 becomes 1.12, and the coefficient of x2 becomes minus 1.07. So on the right here, I'm showing the resulting decision boundary from this classifier. So this line here corresponds to the point where 0.23 plus 1.12 x1 minus 1 point, just clear that a little bit, minus 1.07 x2 is equal to 0. So this is our observation of that transition from the points down here where the score of x is greater than 0 and the points over here where the score of x is less than 0. So the points above that line I'm predicting as being negative points, and the points below the line I'm predicting them to be positive. And you see some interesting things in this simple data set with just simple linear classifier. You see that there's a pretty decent job at separating the positives from the negatives, but there are a few points here where they're misclassified in the training data. So this plus is over here, and this minus is over here. And the question is, can I do better? Can I fit a model with maybe slightly fancier features that does better on this data set? To fit a better model, I'm going to try now what are called quadratic features. So I'm going to consider not just one, x1, and x2, but I'm also going to consider x1 squared and x2 squared. Note that these are not general quadratic features. I'm not considering x1 times x2 or the cross terms, because then it becomes pretty big later on. So I'm just going to do this simple quadratic features. And if I learn a classifier on the same data, I get a really cool decision boundary. And the decision boundary, when I project it into this two-dimensional space, becomes this kind of curved parabola. So the coefficient in this case of the constant becomes 1.68. X1 is 1.39. X2 is minus 0.59. Note that these numbers are different than the one of the previous slide because the parameters are all updated simultaneously with the quadratic terms. And here the quadratic terms become minus 0.17 and minus 0.96. And using these quadratic terms, I get this beautiful quadratic decision boundary over here, which basically says that 1.68 plus 1.39 x1 minus 0.59 x2 minus 0.17 x1, a little cleaner, squared, minus 0.96 x2 squared, this whole thing is equal to 0. And the points now on the left side of the parabola are the ones that have score of x be less than 0, and the points on the right side here are those where score of x is greater than 0. And you get this beautiful curve where, yes, you still make a couple of mistakes, but I tell you, those mistakes seem okay to me. I'm feeding the data pretty well. You never should expect for real data sets to get everything right. And in fact, as we'll see later in this module, getting everything right should be a real big sign of warning for you. But I get pretty good fit, and it looks beautiful. And note, by the way, that the coefficients that I learned over here are pretty good. They look like a natural magnitude, about 1, 0.5, and so on. Now let's see what happens when you do an even higher degree polynomial.